Now that we have all the experiments and the idea that particles and wave both really share each other's properties, so classical particles like the electrons having wave-like behavior, like in the diffraction experiment of Davis and Germer, we can now come up with a updated model of the atom. And this model was developed by Erwin Schrödinger. It's a real physical model of the electron in the atom, and it's really hard to teach it at the level of general chemistry without the necessary math involved. So I'm going to talk about the general features of this model and some of the more important consequences that we're going to look at in this class. The electron itself now is modeled as a wave, and specifically that standing wave that we discussed in a prior video. And the mathematical function that represents the electron is called a wave function, and it has the symbol Greek letter psi. Another name that you might be more familiar is the atomic orbital. So the wave function and the atomic orbital are the same thing. It's mathematical description of the electron's matter wave in 3 dimensions, because the electron has components of both matter, particle, and wave. And the well-known equation that's used to determine the energy of the electron is h hat times psi is equal to E times psi. You don't really need to know how to use this particular equation. It's just shown here as a reference because that's how we are able to get the energy of the electron that are in the different types of orbitals, as we'll talk about later. So one of the things that is hard to explain is just what psi is, what this atomic orbital is. Now, one thing that it is not is that it's not the orbit in the sense of the Bohr model. So if you recall, in the Bohr model, we have the picture that the electron is a particle that circles around the nucleus. You should take that image away from your head now, because that's not what the electron is. The electron is a wave particle that is found around the nucleus. However, as you'll see, we sort of go back and forth between the two models, the quantum model as well as the Bohr model, because the Bohr model is just so much more intuitive compared to the quantum mechanical model, especially at the level of general chemistry. So what's the meaning of the wave function, the atomic orbital? The function itself has no physical meaning, but when you square the wave function, you actually have a physical interpretation of what that value tells you. And this interpretation was given by a scientist by the name of Max Born, so we often call this the Born interpretation of the wave function. When you square the wave function, what you get is the probability or electron density of the electron, which is a measure of the probability of finding the electron in some tiny volume of the atom. So the electron is no longer a classical particle, meaning that you can't just determine where the location and the speed of the electron is. Remember that that's what the uncertainty principle tells us. What we can do now is just know the probability of where the electron might be. So if the probability is high, then it's likely that we can find the electron in that specific location. And if the probability is low, then it's unlikely that we can find the electron there. Now again, the words likely, unlikely doesn't mean that we will find the electron there or we will not find the electron there. It's just that there's some probability that it might not be found there. So let's take a look at how we can represent this chi-square probability density. There are 3 ways to represent this. The first one is just to show it as a density of dots. So in this particular case, I'm showing one of the simplest wave function, which as you'll see later on is called a 1s wave function or the 1s orbital. In this specific wave function, if you plot the probability of finding the electron with more dots representing higher probability and fewer dots representing lower probability, you'll see that the highest probability of finding your electron is close to the nucleus, which is right in the middle there. And then as you go further away from the nucleus, the probability of finding that electron gets smaller and smaller. And R here is just the measure of the radius of the nucleus all the way to the edge of that electron density. You can plot this as a probability as a function of R, and you'll find that as you get closer to the nucleus, which is distance of 0, right, then that probability shoots up as you see in this picture. The second way you represent this probability is by looking at something called the total probability density at some distance from the nucleus. So the first one is just the direct probability. The second one is something we call probability density. And what probability density is just taking a specific volume of the atom and taking the probability in there and dividing it by that volume. That's why the word density is there, because remember, density is mass over volume. So here what I'm showing is a 2-dimensional representation of the atom, but remember the atom is a 3-dimensional object, right? So what I'm doing is just like an onion, I'm creating the shells, probability shells, and then I'm kind of peeling out this shell right here. So this is in a two-dimensional representation. So the nucleus is in the middle. The first shell is right there, and inside there, there's high probability because the dots are very dense. So what I'm going to do is take that and then divide that by that volume, and that would be my probability density, which should be pretty high, okay? And as you can see, as I go further, the volume gets bigger, right? Because I'm at a bigger region here, but then the total probability is going to be smaller. So when I divide those two numbers, I should get a really small number on the outside. I should get a pretty big number as I get closer. The difference though is that if you compare it to this plot right here, if you plot this, it actually kind of drops down when you get really, really close to the nucleus. And the reason is because when you get really close to the nucleus, the volume is so small that the amount of probability inside it is 0. This is the representation that we would look at a lot more in future videos, so you want to make sure that you understand how the probability is represented this way. The third one is something we call probability contour, which is just representing the size of the atom. In theory, the wave function never goes to 0 because remember that it's a probability, so eventually you might have a probability of 0.000001 of finding the electron out here, but it's still not 0. The atoms have a finite size, so we have to figure out where the atom ends. So usually what people do is they would represent the atom as the area that covers 90% of all the probability that we can find. So let's say you still have dots out this way, but then because the 90% is just finished up here, then we kind of draw the atom this way, representing that specific orbital. A second feature of the quantum mechanical model of the atom is the presence of quantum numbers. And so recall that the wave function is a mathematical function. And when you have a mathematical function, you can have multiple solutions to a given function. Sometimes you might have one specific solution, sometimes you might have 2, 3, or more. And so the quantum numbers are basically just solutions to the wave functions. And each of these quantum numbers, though, has real-world meaning. It's not just a bunch of numbers. So we're going to talk about the 3 different quantum numbers that specify the orbital, and later on we'll talk about the 4th quantum number that specifies the electron itself. The first quantum number that we're going to talk about is something called the principal quantum number, which has the symbol n. If you recall, in the Bohr model, he used n as the symbol for his orbit. And that's because the principal quantum number represents the same feature of the atom as the Bohr orbit does. It represents the location where the electron can be found in. The value of n measures two things, which is the size of the orbital. N is closer to the nucleus, then its size is going to be smaller. And secondly, n also represents the energy of that electron itself. I'm using the Bohr model here to highlight what n represents, but of course, again, we're going to bring it back to the quantum model where the electron is actually a wave. A lot of times it's more intuitive to see it in the Bohr model, how we can visualize what the electron is. So in this case, n represents both the size of the orbital as well as the energy of the electrons in that orbital. Okay, so that's what the principal quantum number is. And just like a lot of mathematical solution, they can have specific sets of values. So with the principal quantum number, the values have to be a positive integer, 1, 2, 3, and so on. So it cannot have a value of 0 or negative number. You will hear the term shell or energy level often used to represent n. So all these terms are interchangeable. We might say the electron is in the second shell. That means that the value of n is equal to 2 at that point. The second quantum number is called the angular momentum quantum number. It has the symbol L. So this is a number that is specific to the quantum mechanical model of the atom. There's no comparable number in the Bohr model. This number represents the shape of the orbital. As you'll see, not all orbital is shaped like the one we showed here, which is a sphere. There are many, many different shapes of orbitals that are possible, and it all depends on the actual mathematical function that represents that orbital. So the shape of the orbital is given by this L value. L, just like n, has specific sets that are allowed. So the value of L goes from 0 to n minus 1. For example, if your n value is 2, then your L value is restricted to only 0 and 1. So you can't have any other values. Now you notice that just by going through these first two quantum numbers, that the values are discrete, right? So it's 1, 2, 3. There's no 1.7, there's no 2.1, etc. So it's just 1, 2, 3. So that underscores the importance of the quantized nature of the electron, that the energy must have specific values. values. So the angular momentum quantum number also have specific values like that, 0, 1, 2, etc. And again, it goes all the way to n-1. So n earlier is called the shell, L is called the subshell or the sublevel. Now, we also give specific values of L special names. So if you have L equals 0, that orbital is called the s orbital. If you have L equals 1, that's called a p orbital. L equals 2, that's called the d orbital, and L equals 3, it's called the f orbital. These SPDF orbitals have a specific shape associated with them. The third quantum number is called the magnetic quantum number, or m sub L. So this is the magnetic component of the angular momentum quantum number. And as a result, its value depends on the value of L. It's an integer that can only have value from negative L to positive L going through 0. A quick example, if your L is equal to 1, your m sub L value can be negative 1, 0, and positive 1. What is the physical meaning of m sub L? It tells you the orientation of the orbital. Notice that the orbital can be oriented along the x-axis, the y-axis, or between the x and y-axis, etc. So that's what that m sub L value represents. So all these three quantum numbers that I just mentioned are used to specify the orbital itself, which is the volume in which the electron can be found. So for example, if I say psi 200, I mean that this orbital has n value equals 2, L value equals 0, and m sub L value equals 0. Another way to say this is that this is a 2s orbital. 2 because the 2 represents the n value, s because that L equals 0 is the same as an s orbital. This symbol and that symbol are interchangeable. I like to use the analogy of an apartment building in terms of the interpretation of each of these quantum numbers. So the different floors in the building represent the principal quantum number. So you have different levels in the building. And then the shape of the orbital, which is the angular momentum quantum number, is like the different types of apartments that you have. You can have a studio apartment, a one-bedroom apartment, a two-bedroom apartment. And then the third one is the orientation of the orbital, which you can think of as the orientation of the apartment building. Sometimes that apartment might be facing the freeway, sometimes the apartment might be facing the mountain. There's different orientation of the apartment buildings. And the same with an orbital, there's different orientation of that orbital. All of these different numbers in the end will affect the energy of that electron. And the energy itself, of course, will be very critical in determining what kind of chemical reactions the electrons can undergo, which is really our concern here in chemistry. Now, there is a fourth quantum number. It specifically refers to the electron itself. It turns out that when people look very closely at the behavior of the electron, they found that the electrons shows a pair of closely spaced lines, which means that there's a couple of different peaks in there. And the only explanation, there's two different possible motion that the electron can have when it's in that orbital. So this gives rise to the fourth quantum number, which specifies the electron itself, and it says that in an orbital you can have two types of electron. There is a positive, or what we call upspin electron, and there is the negative or downspin electron. So the quantum number associated with that is called the spin quantum number, or sometimes called the magnetic spin quantum number. The symbol for it is m sub s, and it has two possible values, +1/2 and -1/2 for each of the spin of the electron. Remember that the electron is a charged particle, so when it moves, it generates a magnetic field, and so that's what the two spin numbers represent. Now, because of this observation, which was done by two graduate students, Goudsmit and Uhlenbeck, a famous physicist at the time, Wolfgang Pauli, developed this rule called the Pauli exclusion principle, which states that in one orbital, the maximum you can have is 2 electrons. Another way to state this principle is that no 2 electrons in the same atom can have the same 4 quantum numbers. Each electron has a unique set of the 4 quantum numbers. So it's very much like if you have your driver's license or your student ID number. The student ID number for one student and another student can never be identical. So the same thing here with each electron in an atom. They're going to have these 4 different numbers that specify that electron, and one electron and another one can never have the same set of all 4 quantum numbers. So here we have a couple of questions associated with quantum numbers. First question just asks us to determine the quantum numbers of the first 3 levels. So the first 3 levels is the first 3 principal quantum numbers, and the lowest principal quantum number is 1, followed by 2 and 3. So that's what we're going to do here. Now, when your principal quantum number, or your n, is equal to 1, your L can only be 0, because remember the range of L goes from 0 to n-1. So n-1 is 0, so then it's just 0. M sub L depends on L. So if L is 0, M sub L is also 0, because the range of M sub L L is minus L positive L. So it's minus 0 to plus 0, which is just 0. So for each orbital, you always have m sub s plus minus 1/2, because plus 1/2 is for the up spin of the electron, minus 1/2 is for the down spin of the electron. So in other words, for that first level, you only have one subshell or one orbital, and in that one orbital, you have 2 electrons. When we go to the second level or second shell, now your L value can be either 0 or 1. If it's 0, it's really the same as all the other ones on the top there. So it's just going to be 2, 0, 0, and then plus minus 1/2. However, when L is equal to 1, there are 3 possible m sub L values, minus 1, 0, and plus 1. And for each of these orbitals, there are 2 electrons that we can find in it, plus minus 1/2 for each of those. The total number of electrons, if you add up both this one and these ones right here, gives you 8, and there are 2 different subshells here. And in fact, the subshells are the S and the P, right? 2S and the 2P in this case. If you go to level 3, now you can have L values of 0, 1, or 2. So if it's 0, then your m sub L is 0, and your m sub S value is plus minus 1/2 for that orbital. If it's 1, same as above, you're going to have 3 different possible m sub L values, and for each of those m sub L, you're going to have plus minus 1/2 for each of the orbital. Now for L equals 2, you can now have 5 different orbital values or m sub L values, right? 5 different orientations. Each of the orientation can accommodate 2 electrons. So in total, we have 10 electrons here. And if we add up all the electrons together, we're going to get 18 in this level. And there's 3 different subshells. It's subshell S, P, and D. And that's why we have the 18 total electrons. Next question also in your notes that asks about the name, magnetic quantum numbers, and number of orbitals for the sublevel that has n equals 5 and L equals 1 quantum numbers. When you have n equals 5, of course, you have an option to have L value from 0 all the way to 4. However, they are specifically asking about when the L is equal to 1. So then if L is equal to 1, then m sub L can only have values of negative 1, 0, and 1. So the m sub S is then going to be plus 1/2 for each of those orbitals. So the question is, what is the magnetic quantum numbers, name, and number of orbital? The name of the orbital itself is the 5p orbital, 5 from here and then p from here. And then in the 5p orbital, you can have 3 electrons. So you can draw it this way, and then you can have 6 electrons total, okay?